Hello everyone, this is the penultimate video in this series on the AP Calculus B final, here for semester 1 of Calculus BC. We're going to do questions 32, 33, and 34, and let's jump right into it with number 32. It says to use Euler's method with increments of delta x equals 0.1 to approximate the value of y when x equals 0.13. Then we've got this differential equation and an initial condition. So the Euler's method is an incremental method of approximating a solution curve or a particular solution. Underneath everything that happens, we're making small tangent lines and using the tangent line to make an approximation just a little bit further away from our starting place. So taking a look at this problem, I can see our starting place right over here is the coordinate 1, 2, where x is 1, y is 2. And then we're going to build a tangent line there using this differential equation where dy dx is y plus 2. So if dy dx is y plus 2, what we're going to see is that our delta y, we're going to compute our delta y by doing dy dx multiplied by our delta x. So our dy dx is, let's see, y plus 2 multiplied by delta x, and we already know our delta x is 0.1. Now the only thing that we need to substitute here is our y coordinate, and our y coordinate is 2. So make sure you're substituting the correct y coordinate. So this is 2 plus 2 multiplied by 0.1, so I believe that's 0.4, but I'm going to check it with my calculator because this is the calculator section. So we'll calculate, let's see, 2 plus 2 multiplied by 0.1, and that is 0.4 as predicted. Okay, so the next approximation we're going to make is going to be x plus delta x. So that is 1 plus 0.1, and the new y coordinate is going to be the old y coordinate, 2, plus my delta y, which we calculated at 0.4. And that's equal to, let's see, 1.1 and 2.4. So this says to me that when x equals 1.1, the y coordinate is approximately 2.4. If we were using computers to do this, then we could absolutely make our delta x much smaller. 0.001 would not even be a problem. 0.0001, with a computer's power, that is not a big deal. And so we can get actual solution curves, which would be very close to the actual solution. But as it is, this is just kind of a training class. We're just doing increments that aren't so small, 0.1. And since we're not quite at 1.3 yet, we're going to repeat the process. So it's iterative. We keep on going. All right, so we're going to start now at this value, this x and y. We're going to put that right there. Just like before, my delta x is 0.1. And just like on the previous one, we're going to estimate my delta y by multiplying dy dx and delta x. dy dx is still y plus 2. So here's my delta y, y plus 2. My y coordinate is currently 2.4. So let's substitute 2.4 into our dy dx. And then we'll check and multiply that. That's 2.4 plus 2 multiplied by 0.1. 2.4 plus 2 multiplied by 0.1. That's going to give me 0.44. And then we'll compute the next coordinate. X plus delta x is 1.1 plus 0.1. The y coordinate was 2.4 plus a delta y, which is 0.44. Let's see what that is. Now, I can fool my calculator into giving me something that kind of looks like a coordinate by using the braces. This is technically a list, but for our purposes it serves. So we're going to do 1.1 plus 0.1. And then 2.4 plus 0.44. Let's just make sure that that's what we're looking at. Yeah, 2.4 plus 0.44. And if I use those lists, it's going to give me something that kind of looks like a coordinate. So that's 1.2 and 2.84. And then we repeat the process. This time we're going to start at 1.2 and 2.84, which was where we had left off. My delta x is going to remain 0.1. My delta y is still computed the same way. It's dy dx multiplied by delta x. dy dx is still y plus 2. And my current y coordinate is 2.84. Let's put that here. 2.84 plus 2 multiplied by 0.1. So 2.84 plus 2, and we multiply that by 0.1. That gives me a 0.484 for my delta y. And now I just compute, just like before, x plus delta x and y plus delta y. My old x coordinate was 1.2. So let's put that here. 1.2 plus my delta x, which was 0.1. My old y coordinate was 2.84. And to that, we're going to add 0.484, which was our delta y. Let's go back to the calculator. And again, using the braces, we'll do 1.2 plus 0.1 for my x coordinate. And my y coordinate is going to be 2.84 plus my delta y of 0.484. And that gives me 1.3 and 3.324. To summarize, we're going to say when x equals 1.3, y is approximately 3.324. All right, there is our method. And remember, the key steps here for you is to use a current coordinate, calculate delta x, calculate delta y as dy dx at the current point multiplied by delta x, and then calculate x plus delta x and then y plus delta y. Repeat the process until you have arrived at the correct x and y coordinates. Question 33. The decay equation for a radioactive substance is known to be y equals y naught e to the negative 0.055 t with t in days. About how long will it take for the substance to decay to 64% of its original value? Okay, well, for this one, we already have our equation. So we just need to substitute things. Now, when a substance is at 64% of its original value, and its original value is y naught, maybe that's the thing we should be saying, in this equation for a exponential decay model, we really should say exponential growth and decay model. The exponential growth and decay model, we've got y equals a e to the kt. So if we compare that to y equals y naught e to the negative 0.055 t, then what we see is that a is equal to y naught. And more importantly, our value of k is equal to negative 0.055. And that really does tell us a lot about our equation. All right, well, let's see what we're going to do. If we wanted to figure out 64% of its original value, then 64% is going to be 0.64 multiplied by the original amount, which was y naught. And we're just going to set that equal to our exponential decay model. Right? Okay, that looks great. And if all of this is true, that means that the y naughts are basically going to be, we'll cancel, and we get 0.64 is equal to e to the negative 0.055 t. All right, this is all we need to go on. We're going to take this and put it into our calculator with our solver. So let's get our solver out. Most people are going to have the color screen, so I'm going to do this with the color screen. Make sure you check out the solver on a black and white screen if that applies to your calculator. So to get to my solver, I'm going to do math, scroll all the way backwards until I get to solver. And we're going to do the left side of the equal sign in E1. The left side of the equal sign is 0.64. And then the right side of the equal sign is that exponential. So we'll put this exponential equation here, e to the negative 0.055, and then we'll put a t here. No reason not to. And always make sure that you have these numbers in here correctly, 055, 055. In fact, I shouldn't be checking it with my work. I should be checking it with the problem, 0.055. That looks about correct. Great. So let's get to the solving part. Now for the solving part, I do need to start with a value of t that makes sense. I have a feeling that if I put this negative value and I start solving from a negative value, then I'm not going to get anything nice. I do need to start most likely with a positive result. So let's start at t equals 100, and that should be enough to figure this out to get your calculator to solve. Put a seed value for your variable and push alpha and then enter, and there we go, 8.11431. All right, this means that the substance will decay to 64% of its original value after 8.114 days. Okay, the last problem we're going to do in this video is going to be question 34, where we have a certain population is growing at a continuous rate, so the population doubles every 16 years. How long will it take for that population to triple? This is again the exponential growth model, so let's throw up our exponential growth model. Here's a model that I'm used to, where p equals a e to the kt. And let's see, we know that it's going to double every 16 years. And that means that when t is equal to 16 years, the population is 2 times the initial amount, which is a. Using that, we can solve, or we can put together an equation where the current population is 2a, and that's equal to the initial population, a, multiplied by e to the 16k. We're going to do some light solving here, first by dividing that a out from both sides. And then we'll take a natural log of both sides. The natural log on this right side here, using properties, we can take that 16k and bring it to the front. Remembering that the natural log of e is equal to 1, we get that the natural log of 2 is equal to 16k, or that k is equal to the natural log of 2 over 16. All right, now that I have that, we're going to go to our problem here, and it's going to say, how long does it take for the population to triple? So now we're going to say, what is the value of t when the population is equal to 3 times the initial amount? And we are pretty well equipped to solve this now. Starting with a population equal to a e to the kt, we can get to 3a equals a e to the kt, which means 3 equals e to the kt. Then we're going to take natural logs on both sides. Learning our lesson from previously, we know that when we take our natural log of e to the kt, that's the same thing as kt multiplied by the natural log of e, which again is just 1. So we've got natural log of 3 is equal to kt, and we get that t is equal to the natural log of 3 divided by k. And we'll just set up that's approximately equal to, and we'll get to our calculator now. Okay, on our calculator, we can, once again, go with the value of k is going to be the important one. That's going to be the natural log of 2 over 16. Let's get the natural log of 2, that whole thing divided by 16. You might feel more comfortable with your order of operations if you make that a fraction. So let's do that. Natural log of 2. The whole thing divided by 16. We'll get that same value. That's our value of k. And now to get our value of t, that's going to be the natural log of 3 divided by our value of k. So again, we'll get our fraction bar. We'll get the natural log of 3. And we'll go to our denominator. And then we'll copy, my bad. We'll copy and paste our value of k. Oh, that didn't quite work. Let's start over again. We're going to put the natural log of 3 divided by, let's see, I think that's going to let me do it. Let's try a different tactic here since it's not going to let me paste into a denominator. Let's just take this value here. We'll move to the front here and we'll insert the natural log of 3. And then we'll divide by that result. Yeah, that should work. And that gives me 25.3594. Now I should mention that there is another way of doing this, and that involves using our solver. So let's get to our solver and look at our alternative way of doing this. So alternatively, let's just clear up and get to our solver. And we're going to put our exponential growth equation here. Now let's put P for this first box. And over in the second box, we're going to put A. E to the KT. The only issue we have with this is we do need to start with a value of A. So let's say that A starts at 100. That's always a good place to start. And if A is 100, then the population will double when P is 200. And that's going to happen when T is 16. Okay. We need to do this first in order to get our value of K. So now that I have that, I'm going to put in a value of K, which seems to make sense. These numbers are always kind of small. Also, the fact that the population is growing means that I need my value of K to be positive. So positive 1 should work. And now we'll push alpha, enter. That gives me this value of K. And then now that I have my value of K, we're going to change P to 300 and we'll solve for T. And that gives me basically the same answer. I think that is exactly the same answer. And that gives us the exact same answer. And that's it. We'll see you next time. And for the last video on your AP Calculus B final.